Problem 4. A 10-kilogram runaway grocery cart rolls down an inclined parking lot that is 10 meters long and inclined 20 degrees. A. Is energy conserved or not conserved? Explain. What type of diagram is appropriate for this situation? A work energy or an energy bar diagram? Draw it. B. What is the speed of the cart at the bottom of the inclined parking lot? And C. The grocery cart now runs into a spring with spring constant 250 Newton per meter and compresses it. How much was the spring compressed? So there's two approaches to solving this problem. The first one that I'll do is the work energy theorem approach. A, I'm going to sketch the situation along with a bar diagram. In this process, if the system is only the cart, then there are three external forces acting on the cart. So if I sketch this situation here, I'm going to have an incline and then a flat surface. And on this flat surface, I'm going to take a spring that now is then going to get compressed by the cart. So if I'm looking at my cart, and then I have another cart right here, that's going to run into the spring and compress it here. So when I look at my system here, here's what I see. When the cart is on the hill, once again, my system is the cart, then there are two forces. One of the forces is going to be the normal force, which is external to the cart, and the other force is going to be the force of gravity here. Now, I think I'm going to highlight the incline here to make it clearer to see. So then I can see here is that that's the force of gravity. And in this case, it is going down the incline. So when I'm looking along the incline, you could see that the displacement is going down the incline. So when I look at the cart here, again, there are two forces. There's my normal force, and then there's going to be the spring force that's going to be pushing back on the cart as the displacement is in the opposite direction. So when I look at these two situations here, this is part B, and this is part C. So I need to go in at each of these situations and actually look at them. So let's start with part B of the thing. So in part B, what we're going to do here is that we want to draw a sketch of the situation of a cart rolling down the hill. So if I do that, I'm going to take this piece right here and I'm going to copy it. And so I'm going to place it right here. So the only thing I care about is I care about this situation here. And all I know is that the cart is going to go down the hill. And as it goes down the hill, we see here that the cart is going to come to this spot right here. So what we expect here is that we can see that if I look at this situation, we know that the cart is going to speed up. So I could say that from the work energy theorem, I could say the following thing here. That the network is going to be the work of the normal plus the work of gravity here. And so when I'm looking at this, this is what I'm going to see. This work has to be zero. Why? Because the normal is perpendicular to the displacement. But the reason why this cart speeds up here is because now part of this displacement also has to be going down. So when I look at the work of gravity, I can see here that the force of gravity and the displacement is also going to be down in this case. That implies that the work of gravity must be positive. And because it's positive, that implies that the change in kinetic energy is also positive. So now, writing this in words, this is what I mean by this. The work done by gravity does positive work. Since I have the force of gravity going down, and I know that there's going to be a vertical displacement, and therefore this tells me here that that I'm going to have an increase in kinetic energy, which then tells me that this guy is positive, which then implies that K1 is not the same as K2, so therefore energy is not conserved because I have external forces working on the cart. So if I look at my bar diagram, I know that the cart starts with the kinetic energy of 0 because it starts from rest. Then the work of gravity is now positive. And because it's positive, I'm then going to increase the kinetic energy by this amount. So then the work energy theorem says that the kinetic energy plus the work due to gravity, we already know that this thing starts off at rest. So therefore, the work of gravity then causes the kinetic energy to change. So now I can put this all together. So the work energy theorem shows that the work of gravity is equal to K2. So now, if you come back over here to this picture here, note, so if I set this to be equal to 0, you can see here that there is a height change in this, of this cart going downwards. So then this has to be mg times delta y, which I'm going to write mg times y1 minus 0. That has to equal 1/2 m v2 squared. So what we're seeing here is that because this is the only force is gravity, the masses cancel out. So now I can isolate v2. So if I isolate v2, I get the equation v2 is equal to 2gy1. So now I have the condition to solve v2. Note the height y1 or delta y is not given, but can be calculated. So if I look at this, there's a triangle that is formed. So if I look at my triangle of the incline, it looks something like this. And what we're seeing here, they're telling us that the hypotenuse in this case, which I'll call little h, is 10 meters from there to there. And I know that this height here, I'm going to call y1, we don't know what it is. And of course, this is all measured from y equal to 0. And they tell us that this is an angle of 20 degrees. So now I can use right triangle algebra to solve for this. Now note that this angle is the opposite angle. So the opposite angle, right, since this is the opposite side that we want to calculate, I could then say that the sine of 20 degrees is going to be y1 divided by h, the hypotenuse, which then tells me if I isolate to y1, this will then be h sine of 20, which will then be 10 meters sine of 20 degrees, which then gives me a value of 3.42 meters for y1. Now I know what the height is. Now I can go back and solve for the speed at the bottom. So the speed at the bottom of the hill is v2 2 G y1 square root, plugging in my numbers, 2.2 times 9.81 times the height, which will be 3.42 meters, square rooted, and I get a value of 8.19 meters per second, and that's the speed at 2. So that is what we have. So now let's go to part C. Part C here, now we want to draw a sketch of the cart compressing the spring. So picture-wise, what do we know here? The cart is now all the way down the incline. And so what I'm seeing here is that I have a spring right here. And let's say we're right here. Now let me extend this a little bit. So when this cart gets to the bottom of the incline, it is moving with the speed of v2 right there. Again, for clarity, I'm going to imagine this right here. So now what's going to happen? The cart is going to move. Actually, I don't think I want the speed. So the cart is coming in. And it's going to start interacting with the spring here. So here's my wheel. Oops. Here's my wheels. And all we know is that this cart is moving with the speed of v2 that's the same at the bottom. And then what's going to happen? This cart is then going to compress the spring. And so I'm assuming that I'm going to get maximum compression here. So let me move my cart here again. And at this point, we assume that the speed of the cart is now 0. It gets maximum compression. So when I'm looking at this thing, you could see that the spring has been compressed from its equilibrium point. And then this distance right here is x3. So when I'm looking at this thing, we can see here that the spring force is in that direction and the displacement is in that direction when I look at my cart. Now, I could draw a normal force here, but we already know that the normal force is 0. So now I play the same game as we did before. So there is a normal force, but we know that the work of the normal force is going to be 0 because it's perpendicular to the displacement. So then I start my process here. So my process says that I have this, that the net work is going to be the work of the normal, but we already know that because that displacement is 0, this is going to be the work of the spring. So when I look at the work of the spring, you can see here that the displacement and the spring force are going to be negative. So this guy is negative, which then implies that the kinetic energy decreases. And if the kinetic energy decreases, then we know that the cart slows down. So now, writing this out in words, we then say the following thing, that when I look at this work of the spring, we see that this guy is negative because of this thing right there. So here we go. The work done by the spring does negative work, since we see that these guys are in opposite directions. And because of this, that implies that there is a decrease in kinetic energy. In other words, delta K is less than 0, which then implies that the kinetic energy at 2 and the kinetic energy at 3 are not the same. So energy is not conserved. So in this situation, we can't use mechanical energy. So now what I'm going to do here is that I'm going to come in and now draw a bar diagram, which says here that I have this amount of kinetic energy coming in, which is positive, and I have this amount of work that's negative by the spring, and as a consequence, we know that the kinetic energy at 3 goes to 0. In other words, the work energy theorem says that the kinetic energy minus the work of the spring is then going to be 0. So now that I have my diagram, the work energy theorem allows us to calculate x3, which is the spring compression. So then I go K2, it's going to be the work of the spring. So when I look at the spring, it's going to be 1/2 mv2 squared, and then this will be 1/2 kx3 squared, where I've compressed it from the equilibrium point, which is 0. So now I can isolate x3. So if I isolate, note that the 1/2s cancel out. I have on the left side, I have mv2 squared, and then I have to isolate x3 by dividing both sides by k and then taking the square root. So now if I look at my values, I know that the mass is 10 kilograms. V2 is 8.19 meters per second, and then the spring constant is 250 newtons per meter. So if I plug in these values, I get 10 kilograms times the speed squared divided by the spring constant. And that gives me 1.64 meters for my compression distance.